So here's our setup for two coils with a DC voltage source. We've got the same power supply in the back running through the ammeter, but now the switch I was using before, which was a lever, has been replaced by a tap switch. So this one connects the circuit, closes the circuit, and allows current to flow only while the button is pressed. So if you watch the needle or the ammeter reading here, when I press the button down, we get a current reading, and then as soon as I release, there's zero current. And that current flows into the coil, and again it's winding down on this side, so it's going to wrap around like this. So by the right hand rule should produce a magnetic field to our right, and then we're going to be looking at the effect of that current on a separate coil that's connected to a galvanometer. So this instrument measures small currents. It's very sensitive, but it will let us see if there's current flowing in this coil due to the magnetic field from that one. So to look at the field from this coil, I've got some compasses. These ones on the outside are resting down on the table, and then I've got one on top, and you can see they're all roughly pointed again in the direction of the pencil, which is north. And as soon as I connect the current, they flip around, and now this one on the right is pointing to the right. The one on the left is pointing to the right, so these two are pointing sort of through the coil that direction. But these ones above and below are pointed to the left because the magnetic field lines are coming out of this side, the core of the coil, and wrapping around in that direction. And again, the one on the top is pointing to the left because the field lines are coming out and wrapping over the top towards the back. So releasing, and the compass is reset to north, and then when I turn it on, they switch to show us the direction of the magnetic field. So what we'll do next, now that we know that this coil is producing a magnetic field when it's energized and there's current flowing through it, we can look at the effect on this coil. So I'm going to bring this in, so these are close together, and this galvanometer will show us if there's current flowing in the second coil. So watch carefully as I switch on the current. We get a spike in the positive direction of current in the second coil, but you notice now the current is on in the first coil, so this has almost 2 amps flowing through it, but the galvanometer is not showing anything, so there's nothing happening in the second coil right now. But when I release the switch and the current turns off, you can see we get a negative spike. So I'll do that again. When I turn it on, positive spike, and then when I release, we get a negative spike. So this galvanometer and the current in this coil is only while this one is changing, while it's turning on or turning off. Again, turning on and turning off. So we can repeat that with these a little further apart. You can see we still get this positive spike from the galvanometer and the negative spike when we turn it off, but those are decreased in magnitude now. And that's because the same thing is happening where this magnetic field from the coil is changing, but less of those field lines are going through the second coil now. Some of them are escaping out into space, and so they don't cause as much of an induced current in the second coil. But the third thing we can try is to have this iron tube, and if I put this through the middle of the coils, and we watch the galvanometer now, I'll turn the current on, and we get a big spike where it pegged the meter. It actually hit the maximum. And again, same thing when we turn it off. We get a much larger change, we get a much larger current in this second coil when the iron pipe is connecting the two. And again, that's because the iron pipe sort of traps the magnetic field lines, so much more of the magnetic field lines from this first coil actually link through the second one.